Polycyclic aromatic compounds. Polycyclic or fused aromatic ring systems are when we have multiple rings. These can actually be really dangerous. These compounds are byproducts of combustion, and once they go through the liver, molecules like this become carcinogenic. And so it's molecules very similar to this, these anthracenes, which are actually the causative agents of cancer from smoking, because once they go through your liver, they oxidize and epoxidize. And now it's a flat molecule which can actually squeak into your DNA and chemically react with your DNA. And they're of medium reactivity, which means they don't get destroyed on their way to the DNA, but they can react with the DNA, which makes them extremely dangerous. And so all combustion forms these polycyclic aromatic systems, which is why anytime you have anything burning, you have the possibility of producing carcinogenic compounds. Sources of aromatic hydrocarbons: we have petroleum and coal tar. Coal tar is only a byproduct of coke. Consequently, this method is no longer the principal source of aromatic hydrocarbons, because coke comes from burning coal, and we are rapidly moving away from coal as a fuel and embracing natural gas because it's so much cleaner than coal. Properties of aromatic hydrocarbons: they are nonpolar substances. They are insoluble in water. They're soluble in most organic solvents, and their densities is less than water, so they float on top of water. They burn readily, usually producing smoky yellow flames. And they undergo a lot of substitution reactions, so that they react very differently than just double bonds do. We're going to see halogenation, nitration, and alkylation. Typically use a catalyst. The purpose of the catalyst is that it actually activates the halogen. So in this case, we have our benzene. And let's say we have chlorine. The catalyst binds to the chlorine, making this one more positive. And now we just draw it as the single and double bonds to illustrate our point. The electrons from the benzene attack this positive chlorine, kicking these off, forming this intermediate compound, and then these electrons from the hydrogen come in to fill to get rid of the positive, letting this H plus float away. So you lost a chloride here, and here's your H plus, and that is why you have the hydrohalogen when you're done. The same thing occurs in nitration. It's a little bit more involved. So sulfuric acid is so acidic that it actually acidifies nitric acid. And so when that happens, here, for nitric acid, let's do our Lewis dot structure. We get 6 electrons for each oxygen, so that's 18 electrons for oxygen. You get 5 for nitrogen, you get 1 for hydrogen. So we have 24 electrons to work with. And if we draw that out, 5, 6, 7, 8. 8. So we're starting with nitric acid with a structure like that. And sulfuric acid is so acidic that it actually acidifies the nitric acid. So this oxygen attacks an H+, forming this intermediate product. And now these electrons here go to the oxygen to let water escape, leaving us this compound. So now we have a positive charge on nitrogen, and that's why the electrons will attack it. Giving us nitrobenzene. And so the sulfuric acid is necessary to activate the nitric acid and form that super reactive species so it'll attack. And that's why sulfuric acid is necessary to catalyze this nitration. This is a really dangerous reaction, especially with toluene, because the second and third nitrates actually add faster, and so you can rapidly produce TNT and it can blow up. And so that's a very, very dangerous reaction to run. Alkylation. We have the same type of chemistry as we saw with the halogens. Basically, this catalyst attracts some of this electron density, forming a positive-ish charge here, allowing those electrons to attack, giving us ethylbenzene. And that's a Friedel-Crafts reaction anytime that you add an alkyl group to the benzene group. Oxidation of aromatic side chains. Chromic acid and sulfuric acid are very harsh chemicals, so they will pretty much destroy everything. It doesn't really matter what all is over here. You're going to just be left with one carbon, and it's going to be completely oxidized. And so if you react any alkyl substituted benzene with chromic acid, with sulfuric acid, and heat it, you'll end up with benzoic acid. Very, very, very harsh chemical system. Determine the product for the following reaction. Well, we know this catalyst will attract this chlorine. And again, this is a Lewis catalyst, because aluminum chloride, remember from chemistry 1, will be deficient. Every element wants 8 valence electron, but aluminum chloride only has 6. And so it desperately wants 2 more electrons. So that makes it a Lewis acid. Because it wants the 2 electrons, it'll grab 2 electrons from chlorine, and they'll stick there. And that takes electrons away from the chlorine, which pulls them from the carbon, making the carbon positive-ish right there. And now the double bond can attack there, forming the propylbenzene, or isopropylbenzene, because the bond's in the middle of the propene. And that is the end of Chapter 20, Unsaturated Alkenes and Alkynes.